Hello viewer, it's another opportunity. We're going to have our discussion once again on the program Knowledge Quest on your favorite channel, Hope Channel Kenya. I'm glad to have this time to discuss with you once again. Our subject is physics and our topic is pressure. I'm your teacher Peterson Maranga and I say welcome. Join me as we learn together. Now in our previous lesson we had an introduction to pressure and we we talked about the definition of pressure. We looked at the pressure in the solids and partly introduced the pressure in the liquids. Before we proceed with what we are going to learn in this lesson today, I wish to briefly remind you what we discussed in that previous lesson. So in our previous lesson under the topic pressure, we said that by definition pressure is a force acting normally per given unit area, and so we had this, that pressure is calculated by taking the force, you divide by the area under which the force is exerted. So we said that pressure is a force acting normally per given unit area, and we said that because the force is measured in newtons and the area is measured in square meters, then the SI unit of pressure was a newton per square meter. And of course we mentioned that 1 newton per square meter is equivalent to 1 Pascal. So the SI unit of pressure is newtons per square meter, or at times we can say pascals as the units for measuring the pressure. So that is what we were discussing in our previous lesson. And when it came to the pressure in the solids, we said that in the solids pressure is calculated by taking the force, you divide by the area, just from the definition of the pressure itself. We maintain this one for the calculation of the pressure in the solids, and we mentioned that pressure in the solids depends on two things. Number one, we had the force that is exerted, and then number two, we had the area of contact. So in the solids pressure depended on two things, the force, and we said that the pressure was directly proportional to the force which is exerted. So when the force increases, the pressure also increases, but then it was inversely proportional to the area, meaning what? If the area of contact increases, the pressure exerted reduces. If the area of contact reduces, the pressure increases. So the pressure here was inversely proportional. If the area increases, the pressure reduces. So that is what we discussed last time. And so we had just made an introduction to the pressure in the liquids. And under this, we said that pressure in the liquids also, just like the solids, do exert pressure. And one thing we discussed is that the pressure in the liquids does not depend on the area of contact. But then we had something else. We said pressure in the liquids is obtained by taking the height or the depth of the liquid times the density of the liquid times the gravitational force. This is what we use to calculate the pressure in the liquids. And so from this formula here, we can safely say then that the pressure in the liquids depend on the depth, and then number two, the pressure in the liquids depend on the density, but we do not really say it depends on the gravitational force, because gravitational force is a constant, and so the only things which we can vary for the liquids is the depth of the liquid and the density of the liquid. How can we change the depth of the liquid? We can increase the amount of the liquid in a given container or in a given reservoir. When that increases, the pressure also increases. We can as well vary the density of the liquid. This can only be achieved by using different liquids. For example, in place of water, we can use kerosene, or in place of kerosene, we can use a different liquid. And of course, different liquids will have different densities. And so the moment the density of the liquid changes, the liquid pressure also changes. So we are going to build on this that we were learning last time, particularly the pressure in the liquids. And so we add some things we did not discuss in our previous lesson. So that is what we shall be discussing today, the pressure in the liquids. That is our subtitle. So let me have it here, the pressure in the liquids. Now, I'll have a drawing here. Suppose we have a tin, just a container, and this tin happens to have different holes. There is a hole close to the bottom, and then we have another hole at the middle and another hole at the top. So we have hole 1, hole 2, and hole 3. Then we have an amount of water inside, or just a liquid inside there. Let's have a constant tap up there for continuity of water flow in the container. So we have a tap up there, which is a supply or a source of water to maintain the level of water on top there. Now, if we have this tin on a given table or on a bench, there's something that we are going to observe, that water is going to come to flow out through the holes. So we have a jet coming out of the tin at the lowest hole, and then we have another jet coming out through the middle hole, and then we have another jet from the third hole at the top there. Now we realize one thing, that the jet very close to the bottom of the tin will be thrown farthest. So if you measure the distance from the hole to the point where it is going to land on the table, the distance is the longest for the lowest hole, and then followed by the second hole. The distance is shorter, and then for the third hole, the distance at which it's going to land on the table is very close to the tin. Now, the distance at which the jets land on the table is equivalent to the pressure with which the liquid is coming out through the hole. So then what does it mean? It simply means that the pressure around this hole, the first hole, is more than the pressure around the second hole, and that is more than the pressure around the third hole. And actually this pressure is maximum at the first hole and the minimum at the third hole on top there. And so from what we concluded earlier, we had said that pressure in liquids is given by height times density times the gravitational force. You realize now for the first hole, the depth of the water is from the top here to where the hole is. If we measure that vertical height, this one is more than the second height from the second hole, and the third hole is close to the top, and so the height is minimum. So if we have the third height, the second, and then the first height, you realize H1 is more than H2, and H2 is more than H3. So that means the pressure which is going to be experienced around the first hole is maximum. So pressure 1 at the bottom is more than the pressure at the second hole. That is more than the pressure at the third hole on top there. So again, it leads us to the same conclusion, that for the liquids put in containers, the pressure increases as you move down, as the depth of that liquid or the fluid increases. So an increase in the depth of the liquid increases the pressure that is exerted by the fluid at the bottom. So pressure increases with increase in the depth. That is for the case of the liquids. So as we go down, the pressure keeps increasing. Now, a very important question comes here now. Why do we need this knowledge? Where do we have this idea that when the pressure, the depth increases, the pressure increases? Where is this concept applied? It is commonly applied in the dams, in the construction of the dams and other water reservoirs. Water reservoirs are constructed so that around, if I may have a sketch here, we have something like that one, and so this is the bottom, and this is the wall of that reservoir. The walls of the water reservoir will be constructed in such a manner that at the bottom or near the bottom, the walls are thick. If you consider a region from the midpoint downwards, the thickness of the wall increases. So around the bottom of the reservoir or the dam, the walls are thicker, than they are close to the top or far away from the bottom. Why are these walls constructed so that the thickness increases as we go down? The thickness increases as we go down because already we know the pressure in the liquids will increase. So if this is the water surface and we move down from the surface, the pressure will be increasing. So the pressure around the top here is less than the pressure deep down, and that is less than the pressure at the bottom of the water in the reservoir or in the dam. So if the pressure is maximum down here, then it means we need much thick walls to support the increasing pressure of the fluid or the liquids. So because of that, the dams and the water reservoirs are constructed so that the walls increase in thickness as we go down, simply because the pressure in the liquids also increase as we go down from the surface. If the walls were thin down here, then the increase in pressure may be too much for the walls to support, and so the dams, the walls may break and the water come out. So because of that, the dams are constructed in such a way that the depth, the walls of the dam increase as we go down from the surface. And of course, we did mention last time that the deep sea divers have a maximum depth below which they can dive inside the sea. Below that depth, if they continue with the diving, they may never come out of the water because the pressure acting on top of them will be increasing as they go deep inside the water in the sea. That is factor number one of that is affecting the pressure in the liquids, and that is the depth. The most important thing is that when the depth of the liquid increases, the pressure also increases. Then number two, concerning the same in the liquids, we have the effect of density on the pressure of the liquids. Now, density can only be varied if we use two different liquids. Apparently, we may not be able to change the density of a single liquid, say water. So the effect of density of the liquid can be started using two different setups. We may have a liquid container, say a beaker, and then there is a hole close to the bottom, and then we have another beaker placed side by side with the first beaker. Then it also has another hole at the same level. The holes are the same level across, and then we fill the first beaker with, say, water, and then we fill the second beaker to the same height or depth with another liquid. Let us talk of kerosene. We use a different liquid because we want to achieve different densities. Now, one thing what we are going to learn with this setup is we only see the maximum distance at which the jet is going to land away from the beaker. So for water, the jet is going to come out, it's going to land somewhere on the table. So we have that one. We consider the distance from the beaker to where the jet is going to land, call it y. Let that distance be y. And then we do the same thing for the second one. We place it on a table, and then we consider the distance at which the jet is going to land on that table. So let us call that distance y. So for water, the distance is, let for water be x, and for the kerosene be y. Now what we are going to do is we compare the length x and the length y. One thing that we are going to observe is that x will not be equal to y. The distance x will be different from the distance y there. Now the density of water is approximately, if the water is pure, the density will be 1000 kgs per cubic meters, and if the kerosene is pure, the density will be 800 kgs per cubic meters. Now we see that the density of water is 1000, for kerosene is 800. What does it mean? It simply means water is denser than the kerosene. Already we know from the definition of the formula that pressure in the liquids is equal to H times rho times G. The height of the liquids are the same from the top to the bottom here. This H is the same as from the top to the bottom for the kerosene. So the H is the same for both. And the gravitational force, again being a constant, which is 10, will be the same for both cases. But then the fact that the distance x and the distance y are not the same, it simply tells us that the pressure for water on the left hand side will not be equal to the pressure for the kerosene on the right hand side. Now, ideally, the distance x will be more than the distance y on the other side. So we can say x is not equal to y, but x is greater than y. If x is greater than y, then it means the pressure of the water is greater than the pressure of the kerosene. That is why the jet y is less than the jet x that we are seeing there. The distance from the beaker to where it is landing. So that again tells us this, that because the density of water is more than the density of kerosene, leads us to having a greater distance for the jet for water than the distance for the jet for the kerosene. Then the pressure of the water is more than the pressure of the kerosene. And now, considering that the heights are the same for both cases, this height for water and the height for the kerosene are the same, and the gravitational force on the other side is the same, the only thing which is different are the densities, then we say that the pressure in the liquids vary when the densities of the liquids also vary. In this case, when the density increases, so we say an increase in the density increases the pressure. An increase in the density increases the pressure of the liquid. So if we are going to have different liquids, then the liquid whose density is more will be having a greater pressure at a given level below the surface of that liquid. Now, that is what we have. And now one thing we can again mention here, as much as we are saying that the pressure in a liquid varies depending on the density and the height or the depth of the liquid, there are other things which come out. Like suppose we had a liquid in a given, say, container, say a balloon. Let's have some balloon, and then the balloon is filled with a liquid, and then it is sealed on one side. Then we have holes in different sides of that balloon, and then we try to, there is a hole here, there is another hole, and another hole. We can have another one on top there. We have some 5 holes, 1, 2, 3, 4, 5 of them, and then there happens to be a liquid inside there, and then we squeeze the balloon from sides. We squeeze the balloon inwards from different sides. We are going to see the pressure, the liquid or the water coming out, if that was water, and then we squeeze the balloon from sides, we are going to see the water coming out. So there will be a jet of coming out of the water in that direction. There will be another jet going out in that through that hole. There will be another jet coming out through that hole. There will be another jet thrown through that hole. There will be another one coming out through that hole. So what does it mean? It simply means that for liquids, pressure that is exerted or that is acting in the liquids will be acting in all directions. So pressure in the liquids will be acting in all directions, and like probably in the solids where the pressure will be acting in one direction, that is downwards, because if the weight of the solid is directed downwards, then the pressure of the solid probably will be acting downwards. But in the liquids, the pressure will be acting in all directions and not in one particular direction. So if we have a liquid in a container that can be squeezed, we are talking about a balloon because it is easier for us to squeeze that balloon. Then we are going to have jets coming out through the different holes, meaning what? That the pressure in the liquids will be acting in different directions and not in only one particular directions. Now, with this in mind, we can do a single example, and then from there we can talk about the principle of transmission of pressure in the liquids. That will give us some applications. Now, example, a liquid whose height, a liquid whose height is 76 centimeters has a density of 1,000 kgs per cubic meters. Find the pressure exerted by the liquid. Find the pressure exerted by the liquid at the bottom of the container. Now, a liquid whose height is 76 centimeters has a density of 1,000 kgs per cubic meters. Find the pressure exerted by the liquid at the bottom of the container. Now solution, we say that pressure in the liquids is obtained by height times the density times the gravitational force. Now this will be equal to, in this case the height is 76, so we have 76. Because it is in centimeters, we convert to meters, so divide by 100 times the density of the liquid is 1000, then times the gravitational force, which is 10. So we have these two zeros, and those two zeros, they cancel out. We have 76 times 10 times 10. This will give us 76, two zeros, newtons per square meters. That will be the pressure that is exerted by that liquid at the bottom of the container that is holding the liquid. Again, we did realize that for the liquids, the pressure does not really depend on the area of contact, but then it depends on the two things, on the two factors which we have already discussed. Now, that is all for now concerning the pressure in the liquids. We only talk about the next thing, the principle of transmission of pressure in the liquids. The principle of transmission of pressure in the liquids. So this is a new subtitle. So the principle of transmission of pressure in the liquids. The principle of transmission of pressure in the liquids. Now, already we have talked about the fact that when pressure is exerted in a liquid, or a liquid in a given container will be exerting a pressure at the bottom of the container, and the pressure exerted in that container by that liquid will be acting in all directions. Now, if we quickly talk about what we already mentioned concerning a balloon or something that can be squeezed, and it's having a liquid inside there, and then if it is squeezed from outside, and there happens to be different holes at the different parts, there will be jets coming out in all those directions. It simply means when a liquid is in a container and then there happens to be a compressing force, there is a force acting inside, and there's another force from the other side there compressing the balloon, then the jets are thrown in all the different directions. That simply means that when a pressure is exerted in a liquid, it's going to produce a pressure, and this pressure is going to be transmitted from one part of the liquid to another part of the liquid, and that will be summarized in the principle of transmission of pressure, and that is what we are discussing at this level. Now we are going to have a short break, and when we'll be back, we'll proceed from here. We'll explore more concerning the principle of transmission of pressure and its applications. I pray that you stay tuned, do not go far away. We'll be back shortly. Stay tuned. Dear students, welcome back from the short break. We're going to proceed with what we were discussing. Before we went for the short break, we were talking about the principle of transmission of pressure in the liquids. Liquids do exert a pressure. And if liquids are put in containers, the pressure exerted on them or by them will be acting in the different directions. But now, I want us to look at what we were talking about before we went for the break. Suppose we have a liquid in a given container like that one, and then we compress. We press from the side where there is a compressing force here. There is another compressing force. This force, when it is exerted on the walls of that balloon, it will produce a pressure inside the liquid. This one will also produce a pressure inside the liquid, and that pressure will be transmitted by the liquid so that the pressure will be exerted there on that wall. So there'll be a pressure there, there'll be a pressure here, there'll be a pressure around this hole, and that is what makes the jet to come out. There'll be a pressure down here, and the pressure makes the jet to come out through the hole. There'll be another pressure here that makes the jet to come out through that hole. And now that tells us something, that for a given liquid in a given container, pressure exerted at a given point will be equally transmitted to all the other parts within the enclosed liquid. So this pressure on top, if it is pressure 1, and this is pressure 2, and this is pressure 3, pressure 4, pressure 5, we could be having another one here, there's another pressure 5. As long as the liquid is enclosed within a container and a force is exerted, this force produces a pressure, and the pressure that is produced by that force will be transmitted equally within the liquid, within the entire liquid in that container. So this force also produces a pressure inside here, and this pressure combines with the other pressure, it is transmitted equally in the entire liquid in that container. So we say that for liquids which are enclosed in containers, when a pressure is exerted at one point of that liquid, then the pressure will be transmitted to all the other parts within that particular liquid. So there'll be different locations where the pressure is going to act actually at any given point within that liquid, and all those pressures will be the same. Also, it will be the same value, only that it is transmitted from one point to another. And so that is what we call the principle of transmission of pressure in the liquids. So by definition, the principle of transmission of pressure in the liquids tells us that for an enclosed liquid, maybe I can write it here for you. Let me do away with the diagram. For an enclosed liquid, the pressure exerted at a given point is equally transmitted to all the other parts of the enclosed liquid. For an enclosed liquid, the pressure exerted at a given point is equally, this part here you have to get, we particularly talk of enclosed liquids, and then the pressure exerted at a given point is equally transmitted. These are the key points in that principle. So we have equally transmitted, we have enclosed to all the other parts within or of the same enclosed liquid, and we call that one the principle of transmission of pressure. Now, the principle of transmission of pressure in the liquids will find its important applications in different machines that are known as the hydraulic machines. Hydraulic machines are of different types. I know you have come across things like the car jacks that we use to lift our cars at home when we are doing the repairs for the tires, or we want to lift it up for you to do some particular or some repairs for the cars. So we have hydraulic car jacks at home, or you have seen one. They make use of the principle of transmission of pressure. The cars or the vehicles themselves do have the hydraulic braking system that also makes use of the principle of transmission of pressure. We have a number of them. We have a number of machines that make use of the principle of transmission of pressure. Now, this point I want us to just have an example of such one of a machine we call the hydraulic lift and its applications. A hydraulic lift is used to raise heavy loads. So we have a hydraulic lift. So we have hydraulic machines. In particular, I want us to talk about the hydraulic lift. Hydraulic lift makes use of the principle of transmission of pressure. Now, how does it look like? If we want to do a sketch, we shall have a YouTube. So we have one here. So it is having two arms. One arm is wide, another arm is narrow. So we have a narrow arm on the left hand side, and then we have a wide arm on the right hand side. Now on the narrow arm, this is where we exert our force, our pressure downwards. So we have our force exerting here, and on the other side, on the wide arm, we have the load. Say for example, it is the car you wanted to lift or to raise, so it will be there. That is the vehicle that you are raising on the other side, so it is placed there on top. Then there is a liquid down there. What do we do? What that is going to happen here, in the first arm there will be that piston. This is called a piston, and the piston will be having an area, says area 1, and then we have another piston on the other side, piston 2, and let it have an area, A2. This wide area is where we have the load, the car or the whatever you want to raise, and we are going to exert our force. This force is called the effort. So a hydraulic machine is used to raise some heavy loads that you cannot raise with the without using a machine, because they are quite heavy. So what happens here is this, that when we exert a force on one arm, say the left arm, on the piston, there will be a pressure that is going to be generated here. Because this force is acting on a given area, A1, there will be a pressure that is going to be generated there. The pressure generated will be equal to that force 1, you divide by the area A1. Here we are using the force because we are using the area because the force exerted is going to act on this given area 1. And no, we cannot talk of the pressure of the liquid, the H rho G, because at the top here, the depth of the liquid, actually this is the surface of the liquid, and the H is equal to 0. So we cannot use the second formula, or pressure is equal to H rho G. The pressure that is going to be transmitted there is generated by the contact of the piston on the surface of that liquid, and it will be given by the force which is the effort, you divide by the area of contact. Now this pressure, again, if I may put a subscript there, it will be pressure 1, will be transmitted equally. So there will be a transmission from this part here, and the pressure is going to go the way it is, the same value to the second piston on the other side. And that is what we have already called the principle of transmission of pressure. Now, as it goes to the second piston, something is going to happen that when it gets here, we'll be having the pressure P1 acting upwards. So pressure 1 here is acting upwards, but P1 acting upwards, but that pressure here, it is acting downwards because of the direction of that force. So P1 is acting downwards here, but on the other side, the same P1 is acting upwards on the liquid. Now, as it acts upward on the piston, it produces a force. It produces a force on that piston, and the force is what pushes the load upwards, and in the process, the load will be raised. Now, this is what we are saying, that the pressure on the second piston, pressure on piston 2 will be equal to P1, and that pressure is equal to force 1 you divide by A1. But one thing that we always know, already we have discussed, is that if the pressure is given by the force you divide by the area, if we make force the subject of the formula, it means we multiply by A and A will cancel out. So we have force is equal to the pressure times the area, or PA. Now there is a pressure that is exerted on that piston 2, that is P1, and the area of piston 2 is A2. So that means on piston 2 there will be a force which is going to be generated. Let us call it F2. F2 will be equal to the pressure, which is P1, times what? The area there is A2. So we say that the force on piston 2 then, on piston 2, will be equal to the force 2, which is equal to P1 times A1. But now, P1 is equal to F1, you divide by A1. So force 2 will be equal to F1, you divide by A1 times A2. Now, we take A2 to the left-hand side. So it means we have our F2 is equal to F1 over A1 times A2. So we will divide by A2 on the right-hand side and A2 on the left-hand side. So A2 and A2 will cancel out. We will end up getting the expression that F2 you divide by A2 is equal to F1 you divide by A1. So that is what we call the principle of transmission of pressure in a mathematical form in the hydraulic machines, in the hydraulic lift, and even in the other hydraulic machines. So we have on piston 1, the force exerted is F1, the area is A1. On This pressure generated here will be transmitted by the liquid to the second piston, and as it is transmitted to the second piston, it goes there the same value, the same pressure, because already from the principle, that is what we mentioned. So when the pressure gets to the second piston, the pressure will generate a force. This force F2 is an upward force, and because that force is an upward force, then the force will be used to raise the load which is placed inside there. So the load will be raised because the force F2 is acting on the load, but then in an upward direction. So we say that a small force exerted on one piston produces a much larger force on the second piston. That large force is what will be used to raise the load. So the hydraulic machine simply will multiply the effort. The force that is exerted here is less than the force produced on the second piston, and because that force is much bigger, it can easily be used to raise the load on the second piston. And so we say that force 1 you divide by area 1 will be equal to force 2 you divide by this area of the second piston. And so this is the mathematical expression of the principle of transmission of pressure in a hydraulic lift. Yes, a very simple thing. Now, with this expression, at times we'll be given the forces F1 and F2, but one of the areas is missing. We calculate it. Or we are given one of the forces and the two areas. We find the missing area. And so that is what we'll be doing. An example of a calculation for this hydraulic lift. So the figure, let me maintain the same figure. But now insert some values. The figure below shows a hydraulic lift. So we have that one. Let me remove everything from there. So the figure below shows a hydraulic lift with a load placed on top of it. That is the load. The area here, given that A1 is equal to 2 square meters, that is, no, let me use square centimeters, and A2 on the other side is say 20 square centimeters. An effort of 10 newtons is exerted to raise a load whose value we do not know, F2. So we in this question find the value of F2. We have a hydraulic lift. Now in this case the effort which is exerted is 10 newtons, and the effort is acting on an area of 2 square centimeters, and the effort of 10 is used to raise some load whose value we do not know, and is given as F2. We are finding the value of the F2. So solution, we say that F1 you divide by A1 should be equal to F2 you divide by A2. From that diagram, F1 is 10, so we shall have 10 divided by A1 is 2 square centimeters, so we have 2, but now we convert to square meters, times 10 raised to power negative 4 square meters. This is newtons, should be equal to, we don't know the value of F2, so we have F2 divided by 20, then times 10 raised to power negative 4. Again we convert to the square meters. We want the value of F2. From here mathematically we shall cross multiply, times 20 times 10 raised to power negative 4, and here we have times 20 times 10 raised to power negative 4. The whole of this one cancels with that one. We remain with F2 on the right hand side, so that is F2. On the left hand side, this 10 raised to power negative 4 cancels with that one. This 2 goes here 10 times. Then we have 10 times 10. It gives us 100 newtons. So the value of force 2 on the other side will be 100 newtons. Again we see that the effort which is exerted on that machine is increased in magnitude. By the time it gets to the second arm of the machine, the force has increased from 10 to 100. You will agree with me that 100 is a bigger value that can that can make work much easier than when it was only 10. For all the hydraulic machines, they work such that the final force that is going to do the task intended will be multiplied, and it will be much bigger than what is exerted on that particular machine. That is one way of getting the questions. Now We can as well get a question like this one. I still maintain the same drawing. That the figure below shows a hydraulic machine again. I'll keep some of the values. Let me have this one missing. Now we have the value of this force. Let it be 1,000 newtons. We look for the value of the second area on the second piston. So we shall still do the same thing, that F1 you divide by A1 should be equal to F2 you divide by A2. From the diagram, F1 is 10, so we have 10. A1 is 2, so we divide by 2, should be equal to F2, which is 1,000. So we have 1,000 here, divided by A2, whose value we do not know. We can still work the way it is. We do not convert the two, so that the answer we shall be getting at the end will be in square meters. It is still accepted. So we want A2. This will be times A2 on the left hand side, then times 2, and then times 2 on the right hand side. This 2 cancels with that one. This A2 cancels with that one. So we have 10 A2 is equal to 1,000 times 2. We want to find the value of A2, so divide by 10. This 10 and that 10 goes, so we have our A2 is equal to 0 and 0. We have 100 times 2. This gives us 200 square centimeters. So if the area of the second piston A2 was 200, then the force, the upward force lifting that load will be 1,000 newtons. This is another way of answering the question. But at times we'll be getting questions like that one, and the question does not directly require you to find the value of A2, but you find the radius of the second piston. Find the radius of piston 2. Find the radius of piston 2, or even the diameter, or something like that one. Now, if we were to find the value of the radius of piston 2, first we need to get the area, like what we have here. And now these hydraulic machines put the arm on the left hand side is cylindrical, and the arm on the right hand side is also cylindrical. So if we have an area is A2, then that area 2 is equal to pi r squared. So we have the area, it is 200, should be equal to pi is 22 out of 7, then times r squared. So our r becomes 200 times 7 is 1400, divided by 22. We need the value of r, the square root, and the square root there. So r will be equal to the square root of 1400. You divide by 22, whatever we get will be in centimeters. So as a student, you need to be very careful that when you be answering the question, at times it's not enough for you to find the area A2. Someone may require you to get the radius of that second piston. First, you need to get the area, and knowing that the area is pi r squared, then you can easily find the radius from there. Or at times you can be given the radii. The radius of the first piston, say, is 7 centimeters, and the radius there is 21 centimeters. You find the first two. If this is the radius, you have to first find A1 will be equal to pi r squared. So this is 22 out of 7 times 7 times 7. And on the other side, the A2 will be equal to 22 over 7 times 21 squared. So you get the area A2. Then you substitute in the formula, you use it. So you only need to be careful and see what is indicated on the diagram. It's not always that you'll be given the area. Sometimes you'll be given the radius, sometimes you'll be given the diameter. So you need to first get the area, then you use it in the calculations. So that is the first application of the principle of transmission of pressure. We call it the hydraulic lift. It makes our work so simple. When it comes to mechanics, for those people who repair the cars and the likes. That brings us to the end of the discussion of the first part of the principle of transmission of pressure. In our next lesson, we shall do another application of the same. I request that you stay tuned to Hope Channel Kenya. Till the next lesson, may God keep you, may God bless you. See you next time.